Okay. The operating system, after we have discussed before, okay, there are three kind of category. One is monolithic, okay, in the left hand side. And here, the whole operating system is linked together as a single unit, okay, on top of the physical devices, and then user process can communicate with the operating system through system calls. The second type is modular. Okay, it means you divide the operating system according to their functionality. For example, here are some device drivers. Okay, and then you may have some file systems and with schedule modules or whatever. Okay, so according to their functionality, each module can be used to serve some specific purpose. Okay, again, however, although they are modular, but these modules may be able to dynamic load it into the system. Okay, however, the relationship between these modules may not be very clear. Okay, so that's the for most of the operating system, they organize something like this. Okay, and the microkernel, the last type is the microkernel part. That means we put all these mechanical routines. Okay, they need to be communicate with the physical device together in this microkernel part, and only all those functions in these microkernels need to be executed in kernel mode. Okay, the other functionality of the operating system, for example, file system, the high-level file system module, and scheduler module, and so on, they don't need to be run in the kernel mode because they may not directly use the physical device. Okay, although they serve the purpose of the managing this device properly, but these policies are enforced by mechanism running inside these microkernels. Okay, so that's the third type of operating systems. Sometimes we call it microkernels because they separate these modules according to they use the privileged instruction or they need to be executed in kernel mode or not. Okay, so that's in general we can see these three types of operating system structures. A user process or user program, okay, is a program which can be loaded into operating memory by operating system and then execute their instruction by the CPU. Okay, so the difference between program and the process, okay, in the term in operating systems, they have different meanings. Okay, in general, a program is a file that contains execution code and some static data defined or initialized static and undefined data, but and so on. But a process is a program in execution. That means if a program is been loaded into the system and can be can use CPU to execute its instruction, then this program become a process. So in other words, a program is just a passive entity. Okay, a process is an active entity. So a process will have state, okay, status or state. A program is passive. That means only contain information, but it has no current states. Okay, and each process has its own address space. Okay, this address will contains the state of the processor's register. For example, when a program been executed, you need to use CPU's registers, and the current content of this value of this register, and the memory map, that means which memory are currently allocated or assigned to the particular process. Okay, and so on. So this information we are defined as address space of a process. Okay, and the memory map contains several regions. Okay, it depends on their characteristic. For example, the text region, which is the executable code or machine instructions compiled, linked by the compiler and linker and so on. And data segment or data region are initialized static and global data. Okay, and there is a spatial data segment called the BSS. That's the name defined in Unix. Is uninitialized static data that was defined in the program. Okay, that usually it means Oracle. It is allocated a region of memory for use, but without initialize the content of this region. Okay, those kind of data regions is defined, named as BSS. Okay, so for example, the global uninitialized strings, numbers, and some data structures. Okay, for example, array and whatever. Okay, heap. Okay, it's a growing data segment. Okay, it can dynamically grow. Okay, usually it's used for dynamic allocated memory. That means those memory needed or dynamic obtained, acquired in runtime. For example, in C, if we use malloc memory allocation system code, then those memory allocated through this system code are located in the heap areas. Okay, and last segment is stack area. Okay, used to store subroutine calls, those related data segments required for handling subroutine calls. Okay, for example, the return address, local variable, temporary data, and registers. Okay, and so on. So typical view of a memory map would look like this. Okay, because the heap and stack, they can grow. So in general, we all can land in a contiguous segment of the two ends. The stack grow from top to down to bottom, and heap grow from bottom to up. Okay, and underneath we have a text and data segment in here. Okay, so in general, and a process is organized as a linear array in this kind of layout. Okay, a process during its life cycle, in general, maybe is cycling in 3 different states. Okay, running usually means the process is currently executing its instruction on the CPU. Okay, it's ready. If a process is ready, that means its instruction can be executed by CPU, but currently the CPU is serving other processes instruction. Okay, so ready means all the resource required to execute this particular process is ready. The only missing part is the CPU, so it's ready to use CPU. Okay, the meaning for the ready is something like that. Okay, and then the third state is blocked or waiting state. Okay, usually means this process is waiting for some external event to occur. For example, the I/O operation to complete and so on. Okay, so it is not ready to execute instruction until this event is ready or is complete. Okay, so a simple state transition diagram for a process in its life cycle will be like this. A process may be in running state if it is currently using the CPU, and then when the process require I/O, this process will be moved to blocking state because now you need to wait until the I/O completion. After a process it's required I/O completed, then the particular process will be moved from blocking state to the ready state. Now the process becomes ready to be executed by CPU again. Okay, and also a running process may be preempted and go back to ready state. That means where we were talking about before that a process in general, you will not operation will not assign CPU to a process without setting any time limitations. Okay, if a process we assign CPU without setting limitation, then when the process is early designed, say it enters an infinity loop, then the process will loop in there forever, and that operating system will never, because the particular loop, if unfortunately the particular loop did not use any I/O at all, so then the process will hold in the CPU forever, and no other process will be able to use the CPU. Okay, so to avoid this kind of abnormal behavioral process, okay, designed by application programmers, then most modern operating systems, especially if the system is not for single user but support multitasking, then whenever we allocate CPU to a particular process, we always set a time limit. Okay, so when the limit is expired, the operating system will be triggered to preempt that particular process. So the process, although it did not require any I/O, it will be preempted and moved to the ready state, waiting there to wait for the next time to be scheduled to use the CPU again. Okay, and then whenever the running state, a process is moved out of running state, then CPU become free. Then scheduler will be triggered to select a process from the ready list from, okay, and then move a particular process from the ready state to running. Okay, so a process during its life cycle is circling or change states among these three states. Okay, either voluntarily move from running to block by calling the I/O, or involuntarily by operating system preempted by operating system move from running state to ready. Okay, and so on. Okay, so the module which select the next process from ready state to become running state, we call it scheduler. Okay, to move a process from ready state to become running, we need to be able, operation need to first set the running process current context. Okay, that means it's current program counter or the CPU register, the value of CPU register, and other related to CPU execution attributes. Okay, you need to set those information. Then the process can be moved out of the running state. And after that, when schedule select a new process, a process from ready state, and try to assign CPU to that process, then the selected process is saved context need to be resolved. Okay, so and this context save and restore, okay, can happen by two different ways. One is preemptive. Okay, that means the process is run out of time. Then operating system will take off the privilege to use CPU, okay, by set its state. And okay, this is used. This policy is used by preemptive multitasking system. Okay, the most modern operating system they use these policies because to avoid abnormal processes to run holding CPU forever. Okay, and if a system allow a process to run until it terminate or block on I/O, then this kind of scheduler we call it non-preemptive scheduling. Okay, so the process can only be its context will be saved only when it acquire some I/O services. Okay, then the state of the particular process will be saved. Okay, but either this preemptive or non-preemptive. Okay, to move a process out of running state, we operator will need to set the current context of that particular process. Okay, and then select a process from ready list and restore that particular process context into the CPU. Okay, and operating system keep track all processes by through list of data structures. Okay, and this list may be or lists. Okay, and each element in this list is a data structure. We call it process control block, which contain the attributes of each process. Okay. A typical process control block will contain a process ID or group ID and machine state, CPU register, program counter, stack pointer, and so on, and also the parent list and list of children process. Okay, parent process and children process, and process state. Okay, is in running, ready, or blocked. Okay, and also the memory map and open file descriptor or open file tables. Okay, what kind of file already been opened, and the ownership of the process. Okay, also event descriptor for a process. Every process is currently blocking for some event and signals that have not yet been handled. Okay, so and so or some policy related attributes. For example, the perimeter used for scheduling and memory, okay, management and so on. and also the counting timers, okay, remember time and resource used, okay, and so on. So all these informations are needed for an operation to better manage a process. So, and this information in general kept in the process control block, and this block form a list. Okay, a process in maybe in two different lists or queues. Okay, for example, if a process is in ready state, then in general, operation will keep a ready queue, which may be a linked list, which link all these ready process together. Okay, and if the scheduler is priority, then the first then this queue will be linked together according to their priorities and so on. Okay. And also for different kind of I/O devices, for example, if the system has two disks and two network interfaces, and then for those processes, they are waiting for disk one, then they need to be queued in the block queue associated with disk one, and so on. For those processes, they are waiting for this network interface one. Then they will be linked together in this block network interface ones waiting queue and so on. Okay, so either a process either is in ready queue or in some of the block queues. Okay, so and this information, this PCB used of the data structure represent a particular process. Okay. If we extend this running ready and block state to be more detailed, then the process states can be further categorized into something like this. Okay, the ready state may be contain two substates. One is created, one is ready. Okay, that means a process we mentioned before. If a process is ready, that means it holds all the resource required besides the CPU. Okay. So some operating system, when the process was first created, it did not create it in memory, but created in secondary storage, or sometimes we call it backing store. Okay, so for those operating systems, a process first created in the disk, then that kind of process need to be moved to ready state when those newly created process has been assigned into the memory that become executable by the CPU. Okay, so in general, a ready state may contain, we can extend this to include this newly created process. Okay, and this created may be sometimes we instead of use created, we may use another term. That means it is later we will discuss. Sometimes we call it swap out. Okay, and this ready process is swap in. Okay, so that means it contain is resided in memory, and the process is not in memory, but it's in backing store. It's in this another state. Okay, so and then for the running state, okay, because if a process is running in user mode, that means it's running its application instructions, then it is running in user mode. But a process may need to use operating system service to access some I/O device. For example, you open a file and read something from a particular file. Then the process need to use the service provided by file system, okay, and to actually access the data stored in the disk, okay. So the user process make a system call, and this system call inside the system call will generate a trap interrupt. So the CPU will switch mode from the user mode to kernel mode, okay, on behalf of this user process, okay. And inside this kernel mode, okay, the CPU will execute this corresponding service functions, okay. And then if this service function did not go to use any, sometimes this service function can return immediately. So after this service function finish, the system call will return, and the CPU will change its mode back to the running mode and then continue. Okay, that's possible. Okay, one possibility, because the system call, although it's a system call, it requires the CPU is running in kernel mode, but it did not require to block this particular process, because this system call may not involve I/O request. Okay. For example, some system call, for example, is set a timer, okay, or initialize a timer, and this in general did not cause I/O waiting or block for I/O. Okay, but you just set up something inside kernel mode, and then can be in there. And some system call may make this current running process become into terminated, or some, in Unix term we call it zombie. That means this process is terminated, but the resource assigned to this particular process is not be claimed by the operating system yet. Okay, so only the state is marked as terminated. Okay, so this is also goes through the system code, and then instead of return back to the user mode, because the system code is the exit, is the termination of the user process itself, then the user process will be moved instead of go to the running state in user mode returned by the system call. The operating system will move, change the state of this particular process to be zombie, and marked as all resources associated with this particular process can be claimed back, deallocated from the operating system. Okay. But if the system call invoked by user need to access some I/O device, then the after CPU change to the kernel mode, before it can move, use this I/O device, the process need to be moved to become blocked, because now it's waiting for the I/O device to finish its request. So the particular user process will be put to the blocked waiting queue. Okay. And again, this I/O completion will be the process after it's requested the I/O complete will be wake up and move back to the ready state. Okay. And to move a process inside this kernel mode of the CPU, okay, that means the user process need to be context of user need to be set, and then move to a blocked state. And when the process was rescheduled, okay, that means this, for example, the particular process waiting for disk, and this disk complete, so the process move back to the ready state. and later this process was selected to run again. Then, because this process was terminated or suspended during its last execution from kernel mode, so this register back to the kernel mode, back to the original I/O request or I/O service. For example, it's a disk I/O, then it's inside this disk I/O system call. Okay, the process will restore into this state, and then because this I/O now is completed, so the disk's content, the disk read, will be it's already the data read from disk is already in memory. So then the CPU can issue the return and back to the change mode, back to the running, and then continue to execute user level instructions and so on until next system call or be interrupted. Here, the interrupt usually means the time limit assigned for this particular process to use CPU is expired. Okay, then the user process also need to be interrupted because it's time. This time interrupt. The CPU is changed to the kernel mode, and then inside this kernel mode is a timer interrupt. The CPU, the operation find out, okay, the running process is used up its CPU time. Then we need to preempt this process. Okay, so we set this running process state into, and then move this running process to the ready state. Okay, by through this transition. Okay. It's a preemption by timer. Okay, so that's this is a more detailed state transitions of a process. Okay, because in the past most operating systems designed by the vendors, they on top specific hardware okay, architecture. Okay, so the system call provided by this operation they are all different. Okay, until the Unix they start to propose this idea that portable operating system. Okay, so they try to make this operation to porting from one architecture to another become much easier. Okay, so later IEEE they form a working group and define this standard for portable operating system interfaces of Unix, because there's a lot of version of Unix. Okay, and they find out these different version of Unix, the system code or interface are different. Okay, so the first release is in 1988. Okay, and the latest version maybe in 2017, and this is we call it portable operating system interface of Unix, abbreviated as POSIX. Okay, it defines the application programming interface among this command and utility system utilities for application software to become more portable. So when you write in an application software on top POSIX interfaces, okay, then it's much easier to port this software to other system if that particular system is also support POSIX API. Okay, and most modern operating systems they comply to POSIX in some way. Okay, the POSIX certified operating systems include the AIX, that's IBM's Unix, and HP's Unix, Mac OS, Iris, and Scala's Solaris. Okay, and so on. Okay, and some systems they are not certified, but these we say mostly compliant to POSIX, include this Android, FreeBSD, Linux, Minix, NetBSD, will ESXi, and so on. Okay, and there are also all kinds of POSIX compliant toolkits for Microsoft Windows. For example, this Windows subsystem for Linux supported by Ubuntu, okay, Ubuntu, and Windows C runtime library and Windows Saki API. They are supported by Microsoft. Okay, so these are some POSIX support in Microsoft Windows. In POSIX, they are following system calls defined to support process management. Okay, fork system call is used to create a new process from an existing process, and execute system call is used to load a new program into the current already existing process. Okay, exit tells the operating system to terminate the running the current process. Wait system call allow a parent process to wait for and detect the termination of child processes. Okay, signal is used to let a process to detect signals send designated to this part to itself. And kill is used to send a signal to a specific process. Okay, so these are 5 basic process related or process management related system calls defined in POSIX. Okay, the fork system call is used for a parent process to create a new process, and this new process we call it child process, corresponding to this parent process. Okay, and initially when the child process was first created, these two processes are identical. Okay, so the identical means that their process console block, the content of the process are identical. Okay, the only difference is that they have different process ID. Okay, and their parent attribute may be different. Okay, because the parent of the child is this one, and the parent of this process is its own parent. Okay, other than these two, the other attributes of inside the PCB are almost identical. Okay, so it's a true duplication. Okay, so child is a duplication or a clone of the parent process. Okay, and the only difference besides these IDs, they are different. Okay, the other difference is that this fork system call, although it's called by the parent process, but after the child process was created, both parent and child, their program counter are point to this return part of this fork system call. So they have the same return address. So child process also return from the fork system call. Parent process is returned from the fork system call, and the return value for these two processes are different. Okay, the parent process will return if it successfully create a child. Then its fork will return the ID, process ID of the child process. And the child process will return from the fork by 0. The return value will be 0. Okay, so after the system call returned from the fork, these two processes, because they are identical, they have their same memory map, they execute, they return from to same place. Okay, so to know its load is either parent or its child. These two processes in general, they use the return value to define itself. Okay, if the return is a positive value, that means it's a child process, PID. So it is predictor or parent. So following this fork system call, in general, there are two sets of code segments. One should be executed by parent. Another set of code segments should be executed by child. Okay, well, so by using this return value, then the process would know it's play in the role of parent or child. Okay. If it is play the role of parent, then you execute this portion of the code segment until when it is needed to get the termination information or its child. Okay, for example, the reason we generate a new process usually means we like this code segment of the parent and the child. These two segments of codes, they can be executed in parallel. There's no dependency between these two. Okay, so either way, either one execute first is all right. Okay, semantically, it's all right. Okay, then we can set up by doing something like this. Okay, but however, after these two code segments are finished, the parent process may need to be able, when if the termination information comes in, then parent may be able to continue its operation. Okay, so if that's the case, then parent process should use this wait system call to be waiting here until child process terminate. Then and with the termination status will be caged by returned by this wait system call. Then the parent process would know either the child is terminated normally or terminated abnormally, and decided it continue its execution or do something else to cover the abnormal termination of the child process. Okay, that's in general. But if the child process, after creating child process, if the code segment to be executed by child is too big, or maybe changeable during the execution, or maybe reconfigurable. Okay, different, because depends on different purpose, and then we would like to run a different set of code segments. Then it's possible the code segment associated with the child process may be a set of independent source programs. Okay, it's individually compiled and executable codes. Okay, then after child process was created and identified is running in the code segment of child, then maybe the execute system code can be used to load the predefined reconfigurable code segment, okay, into this child process, okay, to occupy the text part of this program. Okay, let's go back to see the. Okay, here we say a program memory map, a process memory map, in general has this. Okay, so after child process created, because the instruction it need to carry out may be reconfigurable. So every time you fork a child, you need to you ask the child to do something else. Okay, and before you fork a child, you receive an input parameter or whatever, right? And then so after you fork, you find out it's executed in child process. Then you know where to load the new image. So the instruction will be loaded into this part. Okay, but the other remain the same. Okay, the data and the BSS may be different. Okay, but these two. Okay, the new process image will be loaded into this same memory map. Okay, so the process is already there. Okay, but you loaded a new program image into there. That's the functionality of execute, and then execute. Okay. So by doing this, we don't need to compile this code segment may be used by child process with this parent process together. Okay, this kind of design make this reconfigurable become much easy. Okay, so we can let this need to be loaded new program as an input in before we fork a child as an input in this parent process. Okay, before a fork. Okay, and then so after fork, we use this input file name to load a new file to be executed by the child process, and so on. Okay, so this fork, execute, and exit is termination itself. Okay, and wait, the relationship of this system calls something like this. Okay, this if the code segment for child is you don't need the reconfiguration purpose, then you can put them together. So using the if then else or switch to okay together. Okay, but if it's dynamically you need to be dynamically change the code segment of child, then this will be a better way. Okay, and so before this fork, we use an input to submit the purpose for this child creation. Okay, is to run in this program and so on. Okay, and this wait is if the process need to know the child is terminated or not, and then to continue its operation. Then parent can use this system call to get the termination status. Okay, of the child to make sure the continued process operation of this parent's code can be